The derivative as a function. So in the preceding section, we considered the derivative of a function at a fixed number a, and we called this f prime of a. And that definition was the limit as h goes to 0, f of a plus h minus f of a all divided by h. And basically now we're just changing our point of view to now say, what if we don't find the derivative at a specific number a? What if we find the derivative at any number x? So it is the same definition, but now we are going to replace a with x. And then this formula simply becomes a new formula, but really it's the same thing. We just replace the a with an x here and also an x here. But this change in notation now makes us think of the derivative now as not just the instantaneous rate of change at a particular number, or not just the slope of a tangent line at a particular number. Now it represents the rate of change of the entire function f of x. So this function f prime of x can be viewed as a new function, and it is a function that tells us information about the function f of x, where it came from. So we call this new function the derivative of f because it has been derived from f. And we know geometrically it represents the slope of the tangent line to f at any particular number x. To show this relationship a little bit further, let's consider this graph here to be the graph of f of x. And before we look at the graph down below, let's just imagine if we were to pick various points on this function f of x and draw the tangent line to the curve at those points. So you can see, for example, at point A, we have a tangent line that appears to have a negative slope, and we are saying this slope is -1. At point B, we have a tangent line that is flat, so the slope of this tangent line is 0. At point C, we have a positive slope of a tangent line, and we're saying this slope is +1. And then once again, at point D, we have a flat tangent line again. At point P, it's now sloping downwards, and we're saying that that slope is approximately -2/3, etc. So then the graph of the derivative would have to be the graph of a function that has these y values at these particular x values. So for example, point A on the derivative would have a value of -1 because the slope of the tangent line to the function f is -1 at that x value. So at that same x value on the derivative, the function value itself has to be -1. Point B had a tangent line that was flat, so the slope was 0. So at that same x value on the derivative, the value of the derivative has to be 0 because, again, it's representing the slope of that tangent line. At point C, we had a slope of 1 of the tangent line, and now you can see at that same x value on the derivative, the value of the derivative is 1, representing that slope. At point D, the flat tangent line, once again, the derivative is going to hit 0 there because 0 represents the slope of the tangent line. And at point P, at this x value, you can see the value at the derivative is approximately -0.67, and that represents the -2/3. So the graph of the derivative has y values that represent the slopes of the tangent lines to the original function f. So as an example, if f of x equals x to the 3rd power minus x, let's find a formula for f prime of x. So in other words, let's calculate the derivative. So we know f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x divided by h. So just like before, what we need to do is figure out what is f of x plus h. And I like to do this outside of the formula for the derivative. So to find f of x plus h, we have to substitute x plus h in for x in the original function. So we're replacing the x here and the x here with x plus h in both cases. Next, we have to multiply this out, and we've seen how to multiply this expression out in previous lessons. So I'm going to go ahead and assume that we are okay with just writing down the result here. And then if I distribute the negative sign, we get minus x minus h on the end of that. And now we're going to plug this back into our derivative formula. So f prime of x is going to be the limit as h goes to 0. F of x plus h is this expression here. And so we get x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h minus, and then don't forget we have to subtract f of x, which is just the original function. Now when you subtract your original function, please make sure you put that original function in parentheses, because this negative sign here needs to be distributed to each one of those. So we'll go ahead and distribute that negative sign. And so you see that all we had to do here to distribute this negative was change the signs. And that's very important because now this term and this term cancel each other out. And also the positive x and the negative x cancel each other out. And what we have left over on top is 3x squared h plus 3x h squared plus h cubed minus h, all divided by h. And the important thing that happens next is that all these terms have an h in it, and therefore we can factor out an h. So when I factor out an h in the numerator, I get h times 3x squared plus 3xh plus h squared minus 1, and then all divided by h. And this is the very important step. This h cancels out. And now to complete this limit, essentially all we have to do is plug in h equals 0, but I'll go ahead and write down what we have. Okay, and so now we are going to literally substitute h equals 0 into here and into here. And when you do that, those terms, of course, go away, and you end up just getting 3x squared minus 1. And so our original function was f of x equals x cubed minus x. The derivative of that function is 3x squared minus 1. And this derivative function is a function in its own right. Okay, so yes, it tells us information about the original function. It tells us instantaneous rate of change or slope of tangent lines, but it's also its own function. So in the next example, again, we're given a function f of x, in this case equals the square root of x, and we want to find f prime of x. So let's remind ourselves the definition of f prime of x is the limit as h goes to 0, f of x plus h minus f of x divided by h. And so let's go ahead and figure out what is f of x plus h. Now this is pretty simple. If you substitute x plus h in for x here, you get the square root of x plus h. And so our derivative becomes the limit h goes to 0 square root of x plus h minus f of x, which is the square root of x, divided by h. And now if you let h be 0, of course you will get 0 divided by 0. So we need to multiply this by the conjugate of the numerator. And the conjugate is the square root of x plus h plus the square root of x. We do that to the top and to the bottom, just like we've done in previous lessons. And now when you multiply the conjugate, this is a very important part here. You are going to multiply out whichever part of the fraction has the conjugates. So we're going to multiply the numerator times the numerator, because that is the whole point of multiplying by this in the first place. But in the denominator, these are not conjugates, so do not multiply these. So we end up getting the limit, and now we'll do the multiplication. The square root of x plus h times the square root of x plus h is x plus h. Now keep in mind, when you multiply the outside terms and the inside terms, those are going to cancel every time. So the only thing we are left to do here is multiply the last terms together, which is negative radical x times positive radical x, which is negative x. And in the denominator, we have h times the quantity square root of x plus h plus the square root of x. And these cancel out. And what we have next is the limit h goes to 0 of h divided by the rest. And now the very important step where the h cancels out. And this becomes the limit as h goes to 0. Don't forget you have a 1 on top, so this is 1 over the square root of x plus h plus the square root of x. And as the last step now, we can substitute h equals 0 in there, and I'll show this step just to remind you. So this becomes 1 over the square root of x plus 0 plus the square root of x, which is 1 over the square root of x plus the square root of x. And when you add two things together that are the same thing, you get 2 of them. So the answer here becomes 1 divided by 2 times the square root of x. So our original function was the square root of x. The derivative of the square root function is 1 over 2 times the square root of x. And this derivative here, this specific derivative, the derivative of the square root of x, is a derivative worth memorizing. Okay, because you will take the square root derivative many, many times during this course. So it's really great if you can memorize this derivative at some point. And one more example, finding a derivative using the definition of a derivative. So here we have the function f of x is 1 minus x over 2 plus x. So once again, let's remember that f prime of x is the limit as h goes to 0, f of x plus h minus f of x divided by h. And so we need to know what is f of x plus h. Well, again, what you're doing is you're simply replacing x with x plus h. So in the numerator, you get 1 minus the quantity x plus h. And in the denominator, 2 plus the quantity x plus h. Now, please don't leave it like this. In the numerator, let's go ahead and distribute the negative. And in the denominator, you can distribute the positive. And of course, when you do that, this just becomes plus x plus h. Okay, so now we're going to plug this in. So our derivative becomes the limit as h goes to 0, f of x plus h, which is this expression here, minus f of x, which is the original function, and then all divided by h. Now, complex fractions can be kind of complicated, so the next step is very important. What you want to do here is multiply the numerator and the denominator by the least common denominator, which means both of these factors here. So we're going to multiply by 2 plus x plus h, and also 2 plus x to the top and to the bottom. Now, in the denominator, remember, we don't do anything in the denominator. We are just going to write down what we have. So we have h, 2 plus x plus h, and 2 plus x. All the action, so to speak, is in the numerator. So when we multiply these two terms together, the 2 plus x plus h will cross cancel with the 2 plus x plus h, And what we have left is 1 minus x minus h multiplied by 2 plus x. And if you need to pause the video here to work this out yourself to see that this is what we get, then go ahead and do that. Then we are going to multiply this term times these things. And when you multiply here, the 2 plus x cancels out with the 2 plus x, and we get minus. And then we have 1 minus x multiplied by 2 plus x plus h. So again, if you have to pause the video here just to make sure that you understand this particular step, this is a good place to pause it, because most people, when they make a mistake, make the mistake somewhere in this step. Next, we need to multiply this out. So we're going to take everything here and multiply it to each thing here. And then same thing on this side. So we're going to have the limit as h goes to 0. And I'm going to say this out loud here. 1 times 2 is 2. Plus 1 times x. So I'm doing 1 times x. So that's just x. And now I'm going negative x times 2, which is negative 2x. And negative x times x, which is negative x squared. And then negative h times 2 is negative 2h. And negative h times x is negative hx, and I'm going to write that as negative xh. Then we have a minus, and then we're going to multiply these together in the same way. Okay, so I'm going to do 1 times 2, 1 times x, 1 times h, and that is going to give me 2 plus x plus h. And then negative x times 2, negative x times x, and negative x times h, which gives us negative 2x minus x squared minus xh. Denominator is the same. And I want to make a really important point here. We still have the negative in front. Okay, so notice that I didn't do that all at once. I multiplied these first. Now I am going to distribute that negative to everything. And then when you distribute that negative, all these signs are going to become the opposite. So let me write down what that is. Okay, so we can see that we distributed the negative here, which changed all of these signs. And now I'm going to look for things that I can cancel. So let's see, we have a positive 2 and a negative 2. Those cancel out. Positive x and negative x. Negative 2x and positive 2x. Oops, this is incorrect here. Sorry. This is just a positive 2x right there. And then we have a negative x squared and a positive x squared and a negative xh and a positive xh. And so you can see that everything canceled on the top except for negative 2h and negative 1h, which makes negative 3h. And we have the limit as h goes to 0. And now this is the very important step. This h cancels out. And this gives us the limit as h goes to 0 of negative 3 over 2 plus x plus h times 2 plus x. All right. And now we can simply substitute h equals 0 in there. And that gives us negative 3 over 2 plus x times 2 plus x, which is negative 3 over 2 plus x quantity to the second power. And this is the derivative function. Now let's take a look at some other notations for the derivative. So if we use the traditional notation y equals f of x, where x is the independent variable and y is the dependent variable, the most common notation we use for the derivative is f prime of x. Now, if you set your equation up so that it says y equals your function, then it's typical to use y prime or dy dx. So just to make this really clear, if my function is f of x equals x cubed minus x, then I'm going to say my derivative is f prime of x, which would be 3x squared minus 1. But if my original notation was y equals x cubed minus x, it would not be appropriate here to call the derivative f prime of x, because the original function is not named as f of x. So in this case, it would be appropriate to say y prime equals 3x squared minus 1, or you could say dy dx is equal to 3x squared minus 1. So what you want to do is match your derivative notation to the notation of your original function. So in the case where your function is f of x, you should not be using dy dx or y prime. You should use f prime of x. Now there are some other less common notations, and that is these right here. So just know that there are lots of different ways to indicate the derivative of a function. But in this course, these are the ones that we use the vast majority of the time. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval if it is differentiable at every number in that interval. So now we want to talk about the concept of what does it mean for a function to be differentiable? Well, differentiate and derivative essentially mean the same thing. And so when we say that a function is differentiable at a, it means the derivative exists at that number a. Then we have a theorem that says if f is differentiable at a number a, then f is continuous at a. Now, let's talk about some common ways that a function is not differentiable at a. And we'll just take a look at some graphs. So in the first situation here, what we have is what the book likes to call a corner. I like to call this a sharp point. If you have a sharp point on your function, the function is not going to be differentiable at that sharp point. Also, if your function is not continuous at a particular number, it cannot be differentiable at that number, because this theorem says if it's differentiable, then it must be continuous. So if it's not continuous, it cannot be differentiable. So if you have a gap like this, your function is not differentiable at that number. And the other way that a function fails to be differentiable is when you have a vertical tangent line. So that's when your tangent line goes straight up and down. So your graph becomes infinitely steep right there. Okay, so the derivative here would not exist because essentially the derivative there would be infinity. So from an intuitive perspective, the word differentiable means that your function must be smooth, continuous, and not infinitely steep. Right? So it cannot have a sharp point, meaning it has to be smooth. It cannot have a jump in the graph, meaning it has to be continuous. And it cannot be infinitely steep. Now let's talk about notation for higher derivatives. So one way to notate a higher derivative, so that is if you want to take a derivative of your derivative, is you just get this double prime notation. So let's say we have a function f of x. The derivative, or I might call it the first derivative of that function, is f prime of x. Now, if I regard this as its own function and I take the derivative of the derivative, that is known as the second derivative of the original function. And the second derivative has notation f double prime. We can continue this. The third derivative would have the notation f triple prime of x. And then after that point, the fourth derivative and onward would have the notation where you put the number of derivatives in parentheses. So we don't continue the prime notation because it gets to be very cumbersome if you have a lot of primes next to each other. So from the fourth derivative onward, we put the number of the derivative in parentheses like so. Now, if you want to look at the Leibniz notation, which is this kind of notation, once again, your original function now would be called y. Your first derivative we know would be dy dx, or we could call it y prime. Your second derivative, and you can kind of see it here, your second derivative is when you take the derivative, so d dx, of your first derivative. So if you apply this to the top, you get d dy, which they notate d squared y, and then dx dx is dx squared. So your second derivative has this sort of interesting notation, d squared y dx squared, or of course you can call it y double prime. Your third derivative would be very similar. It would be d cubed y over dx cubed, or you would call it y triple prime. And then after that, I can continue with this notation, but we don't say y prime 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 prime. When we get to the fourth derivative, what we do here is we put the number 4 in parentheses pretty much the same way that we did back here. And so these are the notations for the higher derivatives, and typically you won't see too many derivatives past the second derivative, but occasionally we will talk about higher derivatives. So as an example, let's go back to a function that we talked about earlier, f of x equals x cubed minus x. I want to find and interpret f double prime of x. So let's remind ourselves that we already know that f prime of x is 3x squared minus 1, right? We found this earlier in this lesson. So now if I want the second derivative, f double prime of x, I have to take the limit as h goes to 0 of f prime of x plus h minus f prime of x divided by h. So it's the same definition as the first derivative, but when you're finding the second derivative, it is the first derivative that you have in here. So what is f prime of x plus h? Well, f prime of x is 3x squared minus 1. So f prime of x plus h is going to be 3 times x plus h squared minus 1. And if you multiply this out very carefully, so make sure that you FOIL here and then distribute the 3. This is f prime of x plus h. And now we can come down here and we can plug that in. So there is f prime of x plus h minus, now we have f prime of x, which of course is 3x squared minus 1. Again, make sure you put that in parentheses, all divided by h. And then we'll distribute the negative here. And after we distribute this negative, now we will look to cancel like terms. So these terms cancel, these terms cancel, and what we have left over is the limit of 6xh plus 3h squared all divided by h. And now we can factor out an h in the numerator. And this is the very important step where we cancel the h. And this becomes the limit as h goes to 0, 6x plus 3h. And finally, we can plug 0 in here, which of course gives us 6x plus 3 times 0, which is 6x. So again, we had the original function was x cubed minus x. The first derivative we found earlier is 3x squared minus 1. And now the second derivative, we know is 6x. Now, it says to interpret this. Well, the second derivative is the rate of change of the first derivative, right? Because your first derivative is the rate of change of your original function. So the next derivative is just the rate of change of the function that it came from. So the second derivative measures how fast your first derivative is changing. One more comment about derivatives and their relationships. If s equals s of t is the position function of an object that moves in a straight line, we know that its first derivative represents the velocity of the object. So v of t is the same as s prime of t, or ds dt. The instantaneous rate of change of velocity with respect to time is called acceleration, a of t. Therefore, the acceleration function is just the derivative of the velocity function, or the second derivative of the position function. Or in Leibniz notation, acceleration is dv dt, or d squared s dt squared. So acceleration is the change in velocity you feel when you're speeding up or slowing down in a car, for example. So again, if your original function is position, the first derivative is velocity, and the second derivative is acceleration. And this is a very useful application of derivatives. For the next example, let's find the third and fourth derivative of our function f of x equals x cubed minus x. So as a quick recap, we already know that f prime of x is 3x squared minus 1. We found this earlier. And then just a few moments ago, we found out that f double prime of x is 6x. So if I want the third derivative, what I need to do to compute it is to use the definition of the derivative, but when I'm finding the third derivative inside the definition, I will have the second derivative. And so we need to know, what is f double prime of x plus h? Well, again, f double prime of x is 6x. So f double prime of x plus h is 6 times x plus h, which is 6x plus 6h. So this becomes the limit as h goes to 0, 6x plus 6h minus f double prime of x, which is 6x, all divided by h. And you see that it gets really simple to simplify these. Those are going to cancel out, and we get the limit as h goes to 0 of 6h over h. And now the h's cancel out. And then this just becomes the limit of a constant, which we know is a constant. So we know our third derivative is just 6. So what about the fourth derivative? Well, again, the fourth derivative of the function, so f4 of x, if you will be the limit as h goes to 0 of the third derivative of x plus h minus the third derivative of x, and then divided by h. Now, f triple prime is 6. So f triple prime of x plus h is still going to be 6. So this becomes the limit as h goes to 0 of 6 minus 6 over h, which is 0 divided by h, which is 0. So the fourth derivative is 0. And every derivative after that would also be 0. Okay, so the fifth derivative would be 0, the sixth derivative would be 0, etc. But the important point here is each time you're finding the next derivative, you continue to use the original definition of a derivative, but the function inside here is always one derivative less than the one that you're trying to find. And that concludes this lesson.